everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself Professor Anjali Pal. We are both from Civil Engineering Department IIT Kharagpur. We have divided this course into two parts. The first part, environmental chemistry, will be covered by me, and the second part, environmental microbiology, will be taught by Professor Sudha Goel. Now, in my first module, I have covered the acid, bases and salts. In the second module, I have covered chemical equilibrium. In the third module, I have discussed about the chemical kinetics, what is the order, what is the rate, what is the rate expression, then differential rate law and then integrated rate law, how to determine the order, all those things I have discussed. This is my fourth module and this is also chemical kinetics, but here I am discussing the mechanism which is also under the scope of chemical kinetics, and in this lecture I will cover the catalyst. Catalyst also very important for chemical kinetics because it can change the rate of a reaction, it can make a reaction faster or slower. So, this is my module 4 and this is the lecture 18th lecture, and this is chemical kinetics catalysis part A. Now, in this lecture I will cover these topics, the general concept on catalysis, I will tell you what is a catalyst and what are the different types of catalysts or catalytic reactions that I will tell, homogeneous catalysis, then heterogeneous catalysis, then biocatalysis, biocatalyst, and then how the efficiency of a catalyst is determined, what are the parameters you have to consider, that I will discuss, that is nothing but TON and TOF, turnover number and turnover frequency. Catalyst is a very important thing today. In today's scenario, we know that catalysts are very important. There are many reactions which are very slow, that can be made very fast by using some catalyst. They can be some reactions can be done with much less energy or heat if we use the catalyst. Those things we will discuss. Now, here you can see that this is a very important topic today or important discussion. It should be that green chemistry. What is green chemistry? There are two persons, Paul Anastas and John Warner, in 2000. You see, they have given these 12 principles of green chemistry. They are very famous persons, and what are the two principles? You can see prevent waste, then design safer chemicals and products, design less hazardous chemical synthesis, use renewable feedstock, use catalysts. So, you can see here the catalysts are also under this green chemistry principles. Okay. Then maximize atom economy, avoid chemical derivatives, use safer solvents and reaction conditions, increase energy efficiency, design chemicals and products to degrade after use, analyze, like this there are. So, you can see that use catalyst is also there in this principle. Not only this, you can see here, if you research minded or if you want to do research, if you go to the journals, then you will see there are many journals, they are dedicated for the catalyst or catalysis. Okay. So, there are very good journals like from SCS, from LCVR, from RSC. You will see that there are many journals just dedicated on catalyst or catalysis. So, this is really a very important field today. Now, catalyst, the first thing it is a very simple thing, simple in the sense all of you know. H2O2, hydrogen peroxide. Okay. In our school days also we have learnt that H2O2, many different purposes we can use H2O2. Say for example, if you think about environmental pollution, then we can use H2O2 to degrade pollutants, organic pollutants. And then if we think about our daily use, then antiseptic, it can be used as antiseptic wash in surgery, in dressing wounds, in surgery, in dressing wounds, then mouthwash as a bleaching agent. So, they have several applications, okay, in our daily life also. Now, if you just keep hydrogen peroxide, if you take a say watch glass, okay, and you put some hydrogen peroxide there, what you will see? You will not see much, means H2O2 will decompose to H2O and water, and some heat will be produced. You can see it, but not very vigorous way you will see. But say for example, you take some MnO2, you know MnO2 is pyrolusite natural ore. So, you can take some MnO2 in a watch glass and put the H2O2 there, then you will see vigorous, very vigorous reaction that is happening. Okay. So, that is nothing, that is just due to that MnO2 is a very good catalyst for decomposition of H2O2. Okay. Now, here it is shown that at ordinary temperature the reaction is very slow, that we can observe also at ordinary temperature, but in presence of finely divided metals or MnO2 the reaction is vigorous. So, what you understand from here, by using some catalyst we can make a reaction faster. Okay. So, that is the catalyst. Okay. Now, at ordinary temperature, but in presence of acids, say for example, phosphoric acid, the reaction is retarded. Okay. So, this is also a catalyst. Okay. Phosphoric acid is also not only catalyst will only make the reaction faster, but it may make the reaction slower also. Then it is also catalyst, it can be said inhibitor or it can be said negative catalyst, something like that. So, that means it is a substance which affects the rate of a reaction by its presence. Okay. Now, if I do not know whether you have used H2O2 in your lab or not, but if you see the bottle of H2O2, then you will see that it is kept in black colored bottle and plastic bottles, okay, or brown colored bottles, plastic bottles. Why it is so? Why not in glass bottle? Why not in colorless transparent type bottles? Many reagents we keep in those types of bottles. Here actually you know that H2O2 is decomposed under heat or under light also. Okay, that is why it is kept in black colored bottle, because if you keep it under normal light, then some diffuse light is also can bring can cause the decomposition of H2O2. And another question is there, why H2O2 the strength of H2O2 decreases with time gradually, okay, and it has to be standardized. If you are using the H2O2 bottle for long time, say for example 2-3 months, then in the day 1 and in after 3 months, that is the 90th day, you cannot tell that okay, the H2O2 strength is the same, because continuously it is decomposing, and that is why time to time you have to determine the strength. Okay. But there is some standard procedures by which you can determine the strength of H2O2, that you have to do, otherwise you will come into a wrong conclusion, because your strength is not not the same and it is changing. So, your conclusions will be wrong. What is the better way? Then because H2O2 in all laboratories you will see that H2O2 is present. So, then how to keep it, where to keep it? It has to be kept in the refrigerators. Okay. Then at lower temperature the decomposition becomes slow. Okay. Now, catalyst and catalysis, who has said this, who has coined this term, who has said first this word catalysis? This is nothing but Berzelius. You all know the name of Berzelius. Okay. So, he has first coined the word catalysis. he observed, what is his observation is that he observed that many chemical reactions were accelerated by the presence of some foreign substance, okay, by some foreign substance that is not taking part in the chemical reaction, it is foreigner. Okay. It appeared that they did not take part in the reaction. He described the process as catalysis. At the end of the reaction, the foreign substance remained unchanged in mass and in composition. Okay. So, foreign substance should have some speciality. What is that speciality? There is no change in mass. After the reaction also you will see there is no change in mass, and you will say that composition is also not changed. Okay. But sometimes some morphology may change, sometimes morphology is changed. Okay. So, that foreign substance is called as catalyst. Okay, catalyst. Now, there are different types of catalyst. As I told you that there may be positive catalyst. Positive catalyst means it makes a reaction faster. There may be some negative catalyst which is also called inhibitor. Okay. So, there is a very good example of formation of HCl from hydrogen and chlorine in presence of active charcoal. So, charcoal is also, it is a solid substance. So, it can act as a very good catalyst also. Okay. And negative catalyst, you can, I have already told you that we do not want that when we store H2O2, then we do not want that it decomposes, right. So, if we do not want that, then what we will do? We will use something which is a negative catalyst, that means which will slow down the process of decomposition. Okay. So, that is done. Phosphoric acid can do that. Now, autocatalysis, it is a very good experiment. Okay. It is the experiment of determination, means determination of the strength of permanganate. You know that permanganate KMnO4, you know it is a pink colored substance, and when the solution is prepared, it is pink colored solution or purple colored solution, and the strength, even if you take the proper weight and prepare the solution, then also strength is not means actual strength. Okay. That is why it is called a secondary standard. You have to determine the strength by using another standard, and that is called the primary standard. So, primary standard is something whose strength does not change with time and which you can take the weight properly. Okay. So, what is that here? If you see the reaction, this is the reaction between permanganate and acidic condition, and this is the nothing but the oxalic acid. Okay. Oxalic acid, this is a redox reaction. Okay. Here permanganate is an oxidizing agent, it is going to Mn2 plus, and oxalate is a reducing agent, it is going to CO2, and it has no color. Okay. Oxalic acid has no color, but KMnO4 has color. So, if you take KMnO4 in a burette and you take oxalic acid in presence of acid, you take in a conical flask, and if you start your titration, so you add drop by drop the permanganate into this oxalate solution, then oxalic acid solution. Okay. So, then what will happen? You will see that permanganate color should be discharged because it is going to Mn2 plus. Okay. So, color will be discharged, but what you will see that in the initial stage of addition, first few drops of addition, you will see that color is not going very quickly. Okay. So, it is staying, the color is staying, although color should go immediately, but it is staying. Okay. Why it is so? Because this reaction is slow reaction, but then after addition of few drops, you will see that reaction has become faster. Okay. Color is going fast. Why it is so? Why it is so? Why initially it is not going fast, and after few drops of addition, then you see that color is going very fast. Why it is so? This is because this Mn2 plus which is produced in this reaction, this is acting as the catalyst. Okay. So, here catalyst is the Mn2 plus, and this type of reaction is called autocatalysis. Auto means self. Okay. So, the product itself is being is acting as the catalyst, that is why it is called auto catalyst. Okay. Auto catalysis. Now, this is induced catalysis. What is induced catalysis? You can see here, this is the arsenite and this is the arsenate. Okay. Arsenic 3 plus state and here it is arsenic 5 plus state. Okay. Arsenite and arsenate, this is an oxidation. So, in presence of oxygen this can happen, but you will see that this is not happening. Okay. But if you add sodium sulphite is also oxidized to sodium sulphate, but you will see that once you add this thing the reaction occurs. Okay. So, that means what? It is the induced catalysis. Induced, you have induced some catalytic reaction, catalysis. Okay. So, there are different types of catalyst and catalytic reactions. Now, characteristic of catalytic reaction. So, catalytic reaction, how is the catalyst? What is the characteristic of a catalyst? Okay, that we have to discuss. A catalyst can only change the speed of a reaction. So, a reaction speed only changed by a catalyst. It cannot change the final state of equilibrium. Okay. So, it cannot change the final state of equilibrium. Now, you know what is equilibrium, you know what is equilibrium constant. Okay. All those things I have already discussed in my module 2. So, that it cannot change, you have to remember this. Okay. It helps to attain the equilibrium quickly, means only the rate is changed by a catalyst, but other thermodynamic parameters cannot be changed. It accelerates both the forward and reverse reaction to the same extent, that is why it cannot change the K, equilibrium constant. A catalyst provides an alternative path, how it is changing the rate. Okay. It is providing by, say for example, I want to go to one room, there are two routes, one route takes longer time, another route takes shorter time. So, route is different. So, it is going through a different route, that is why it is becoming faster. Okay. A small amount of catalyst is required. Catalyst amount is very small, that is required to accelerate the reaction. Okay. And a catalyst remains unchanged in mass and chemical composition, that I already told you. At the end of the reaction, it remains unaltered, the mass and the chemical composition. However, the physical nature may change. Sometimes you may use crystal, but it will go to amorphous stage, like this, that thing it can happen. And a catalyst cannot start a reaction. So, here I have given a very nice example that we see in the school days. Okay. This is the laboratory method of oxygen preparation. What we do? Potassium chlorate, you know, potassium chlorate we take and MnO2, MnO2 is catalyst. So, we mix these two very well. Okay. We grind it both the things together. Okay. Then we heat at this temperature, okay, 250 degrees centigrade in a hard glass, in a test tube, hard glass test tube. After that, when oxygen is prepared, we collect it, collect the oxygen. So, that is the laboratory preparation. But you can tell me that if I do not use MnO2, if I just take KClO3, then whether oxygen will be produced or not, if I heat it, whether. So, it can also happen, but it takes higher temperature, much higher temperature. Now, you know that energy, we want everything fast and we want the energy efficient way. Okay. Energy is a very important thing today. Okay. We always want everything energy efficient. Now, catalyst is helping us in that way. Okay. See here, it is taking, means at very high temperature it is happening, but here it is much lower temperature. So, catalyst is doing that function, okay, or helping us in that way. Okay. Now, classification of catalysis, you know, there are many different kinds of catalysis like H plus acid catalyzed reactions we have seen. We have seen base catalyzed reactions also, Lewis acids, you know, aluminum chloride, you already know that this in acid base chapter I have told that what is Lewis acid, what is Lewis base. Now, aluminum chloride, you know, Lewis acid. So, this is also can act as a catalyst. Now, some organometallic complexes, you know what is organometallic compound, organometallic where the carbon metal bond is there, that is called organometallic. Okay. So, Grignard reagents for example. So, organometallic complexes that can act as a catalyst. Organic and inorganic polymers, they are the support material. So, they can act also as catalyst. Now, enzymes means biocatalyst, you know that in our body system there are so many enzymes, you will learn in a very nice way in the environmental microbiology that enzymes, their function and all. So, enzymes, you know, very complex molecules and they have specific sites to carry out specific reactions. Okay. So, enzymes are also good catalysts. Then how to classify them? How will you classify? Okay. So, mainly the catalysis, the catalyst or catalysis is divided into three classes. So, one is the homogeneous catalysis, another is the heterogeneous catalysis and biocatalysis. Okay. So, I will discuss those things, but what is catalyst promoter and what is catalyst poison? Okay. We know catalyst, but what is catalyst promoter? Very good example, that is the ammonia synthesis. Ammonia synthesis we have seen. When I discussed about Lahr-Sattler principle, there I have discussed that hydrogen and nitrogen they can react to form the ammonia, and it needs high temperature, high pressure. I also told that there one catalyst is needed, that is finely divided iron. Okay. But with iron, if you use trace amount of molybdenum that is along with the finely divided iron, then it can enhance the reaction rate significantly. So, molybdenum actual catalyst is this one, this finely divided iron, but molybdenum is a catalyst promoter. Okay. It can enhance the rate further. Okay. So, this is a promoter. Now, poison, what is poison? That is anti-catalyst, that is a poison. So, poison means it inhibits the catalytic action, it poisons the catalytic action. Okay. Substances which reduces the catalytic activity. For example, in the contact process of H2SO synthesis, you know that contact process and chambers process, all those processes are very important for sulfuric acid synthesis, right. So, there platinum is used as the catalyst, but if there is trace amount of arsenious oxide, then it can destroy the catalytic activity of the platinum. Okay. So, this is a poison. We all know poison, what is poison? So, it is poisoning the catalytic activity, it is poisoning the catalyst. Okay. So, this is the catalyst poison. Now, what is homogeneous and heterogeneous catalysis? Some examples I will tell. In homogeneous catalysis, the catalyst is in the same phase as that of the reactants and products. So, it is a homogeneous condition, it may be anything, it may be gas phase, it can be liquid phase, but everything is there in the same phase, catalyst and then substrate and then products, everything is in the same phase, then it is the homogeneous catalysis. There are many examples, I have only taken a few. Okay. This is the biodiesel production, very important topic today, biodiesel production, trans esterification of fatty acid triglyceride. Okay. You know fatty acid, you know what is fatty acid triglyceride. With methanol catalyzed by OH minus, that is this is an important reaction for diesel production. Their catalysis is OH minus, means base catalyzed reaction. Okay. And this I already explained, pseudo unimolecular reaction, pseudo fast order reaction. There I have told you that cane sugar when hydrolyzed, this is in presence of acid. So, it is acid hydrolysis. when it is hydrolyzed to glucose and fructose. There I have told levulose, but glucose and fructose, then inversion of cane sugar happens, hydrolysis with a hydrolysis. So, this is catalyzed by acid. So, it is acid catalyzed and everything is there in the liquid phase in solution. So, it is a homogeneous catalysis. Chamber process of sulfuric acid synthesis, there nitrogen oxide is used as catalyst to convert mixture of SO2 and oxygen and water vapor to H2SO4. This is a very important method of production of H2SO4. Okay, there nitrogen oxide is there. Okay, nitrogen oxide is used as catalyst. I will tell you the mechanisms later, but these are just the examples. Now, in heterogeneous catalysis, the catalyst and the substrate are in different phases. One may be solid, one may be solid, one may be liquid, or one may be solid, one may be gas. Okay. So, this is gas solid or solid liquid, something like that. Now, finely divided iron in ammonia synthesis by Haber process. Obviously, this is this is ammonia is gas phase and iron is in solid phase. So, it is an example of homogeneous catalysis. Active charcoal in the formation of phosgene, it is a very poisonous gas, phosgene. So, it can be synthesized from carbon monoxide and chlorine. So, there active charcoal is used. So, all are gas, but this is the solid. Now, platinized asbestos for the conversion of SO2 to SO3 in H2SO4 synthesis by contact process. This is another process of H2SO4 synthesis. There platinized asbestos is used. So, it is also heterogeneous catalysis. So, for heterogeneous catalysis, the advantage is that, what is the advantage? The catalyst can be easily separated from the reaction mixture. Okay. So, this is a very good advantage. In the homogeneous catalysis, after the reaction, how can you take out the catalyst? Although catalyst is doing many cycles, running many cycles, but still at the end, if you want to recover it or if you want to separate it out, then how will you separate? This is a problem, but for heterogeneous catalysis, this problem is not there. Now, when there is a catalyst or there are two catalysts, how to know which catalyst is better? So, to know this, we have to consider two things. One is the turnover number, another is the turnover frequency. Both are similar, turnover number and turnover frequency. Now, catalyst turnover number and turnover frequency are two important quantities used for catalyst efficiency. Okay. So, and they are defined in different ways in homogeneous catalysis, in heterogeneous catalysis, in biocatalysis. The definitions of TON is different. What is this? In homogeneous catalysis, we define TON as the number of cycles that a catalyst can run through before it gets deactivated. The how many runs it can go. Okay. So, before it gets deactivated, that is the homogeneous catalysis, and TON is the number that is TON is the number of X molecules that one molecule of catalyst can convert into Y molecules. Say for example, X is going to Y. So, how many X molecules are converted to Y molecules by one molecule of catalyst? That is the, for homogeneous catalyst, that is the definition, and TOF is nothing but TON by time. Okay. So, similar, it is similar, but this is also time factor is coming in TOF. Okay. Now, heterogeneous catalysis, TON and TOF are defined per active site, per active, because it is solid. If you think about it is a solid, so active sites will be there, or per gram of the catalyst. So, here it is defined in this way. So, the that means how many number of molecules it is converting per gram of catalyst. Okay. So, that is the heterogeneous catalysis we use, and it is difficult to know exactly how many catalyst molecules are there on the surface. That is why it is defined in this way, per gram. Okay. Because we know how many sites are there, exactly how many catalyst molecules are there, that is also very difficult. How many sites also, it is very difficult. Per gram is easier, most of the cases we see per gram. Okay. Now, biocatalyst again definition is different. TON and TOF are defined by the rate measured when all the enzyme molecules are complexed with a reactant divided by the total enzyme concentration. So, this is also different. So, there are different ways to tell the TOF and TON, but there is the relation you have understood that what is TON and what is TOF by time, TON by time is TOF. Okay. Very important. Any good papers also you will see that they have calculated these values, these two values. Now, industrial, there are many industrial applications also for catalyst. Say for example, this I have already, this is nothing but the Haber process, you know, it is the it is also nitrogen fixation. When I will talk about nitrogen cycle, then I will again tell it about this. Now, this is you know, for ammonia fertilizer synthesis, ammonia is so important. So, this is important, but you know that when Haber process, the yield, if you know the yield, you will be surprised to know, although it got the Nobel Prize, the yield is only 7%. Okay. So, after such a huge temperature and pressure application and even catalyst, you see the yield is very less, but still it got Nobel Prize. That is very interesting to see. That time it was so much important. Now, hydrogenation of unsaturated oil and fat. So, unsaturated oil and fat, this double bond is there. So, the hydrogenation can be done, okay, in presence of Raney nickel or nickel, finely divided nickel as catalyst. Okay. So, this is also heterogeneous catalysis. Synthesis of HCl from hydrogen and chlorine, this already I have told, active charcoal, this is also very important procedure for HCl synthesis. Now, oxidation of ammonia to nitric oxide, ammonia oxidation by oxygen to nitric oxide, then nitrogen dioxide, then nitric acid. This is Oswald process. Here also platinum gauze is used as the catalyst. These are all industrial large scale production. Okay. So, here you see so much application of catalyst. So, if you can develop a very good catalyst, even patent you can take, and that can be really useful for some good synthesis, then it is very, there are many awards also for catalyst synthesis. Here you can see that oxidation of sulfur dioxide to sulfur trioxide, this is also for sulfuric acid preparation in contact process. Platinized asbestos or vanadium pentoxide is used as the catalyst. So, I have picked up only few, but there are so many. Now, what is catalytic converter? You know that this is most important, although I have not described much, but you can see that most widely used chemical catalysis is in everyday life is the catalytic converters installed in the exhaust of automobiles. What is happening in the automobiles? We know that in the automobiles you use the gasoline, that is the nothing but the hydrocarbon. So, hydrocarbon is oxidized to carbon dioxide and water, but if it is in incomplete combustion, then it goes to carbon monoxide, and some of the gasoline is escaped out. Okay. So, it is polluting our environment. So, what should be our goal? Our goal is to use some good catalyst, so that it goes to complete oxidation, that means it goes to carbon dioxide and water, and for this purpose we use some catalyst as platinum. Okay. There is another thing is going on when we use the gasoline there in the vehicles, automobiles. What is happening? The air, when air is burned at high temperature, what is there in the air? There is the nitrogen and oxygen. So, they combine to form the nitrogen oxides, okay, NOx, they form the NOx. So, when NOx is formed, that is also polluting. So, if we can use a very good catalyst, then if we can reduce the NOx to N2, then it can go back to the atmosphere, and then it will be good for environmental purpose. So, for that reason in the catalytic converter platinum and rhodium is, there are many others, but these are most common. Platinum and rhodium are used, are deposited on a fine honeycomb mesh of alumina, to give a large surface area. So, for catalyst surface area is also very important, that increases the contact time of the exhaust gas with the catalyst. And then what is happening, our desired thing is happening. Then platinum and rhodium, those are the two catalysts, but they are used for different purpose. So, in one case we need to oxidize the gasoline to carbon dioxide and water, in another case we want to reduce. Okay. So, but these two catalysts are used. Catalytic converters can be poisoned, but those catalysts are easily poisoned by certain metals that block their active sites and reduce their effectiveness. Okay. Lead is one such metal. So, unleaded petrol must be used in automobile. Now, it has come in the market, unleaded petrol, because lead is very dangerous, not only for health purpose, but also as a poison in this type of catalytic converter. So, unleaded petrol must be used in automobiles with catalytic converters. Okay. So, this is briefly I am telling you, just giving the brief, it is a large field, okay, the catalytic converter, but it is daily basis, this is a good application of catalyst. Now, the references I have shown here, the same references actually, this book and these two are books, all three are books actually, but this book is very good, this is also good. Here it is for catalysis, it is also some parts I have collected, some information I have collected from these books. Okay. So, as a conclusion I can tell that in this lecture we have discussed about different types of catalysts and their industrial applications. Various catalytic reactions have been elaborated, the turnover number, turnover frequency of a catalyst is discussed for various types of catalysts. So, these are very important for catalysts. Thank you.